Okay, hello everyone, especially the young future physicists. So I'm Wen-Chin Wu, the chairman of the physics department at National Nobel University. So it's my honor to introduce our honorary speaker, Nobel laureate, Professor Douglas Osheroff from Stanford University, to give us a talk today. So let me give a brief introduction for Professor Douglas Osheroff. Professor Osheroff received his bachelor degree in 1967 from Caltech, and then PhD degree in 1973 from Cornell. At that time, Cornell are full of low temperature scientists, including my boss, Professor Aaron Griffin. And who received many prestigious awards and titles. The renowned one, of course, is the Nobel Prize. In 1996. For his low temperature discovery of the many bases in helium 3. The famous work. So he's going to talk about how advances in science are made. I think he prepared a very nice picture, and he just put the title just away from this nice picture. To see the golden age. And so let's give him a big hope, and then welcome Professor Osheroff.
Well, I'm honored to be here. This is such a spectacular competition, and I dare say I'm very happy that you're competing and not me. It's a fantastic set of events, and I look forward to seeing what happens tomorrow. By the way, is it the 26th or what is 26? So I did get that right. That's amazing. I'm not good at those things anymore. Anyway, so let me first say that this is a talk that's grown up over time, and so there's a lot, I think, a lot of wisdom, I hope wisdom in it. I don't know if you agree with me, but that's what it's all about, supposedly. So this is, you have to realize that I am I'm a passionate photographer. In fact, maybe sometimes more passionate than makes any sense. This is, of course, the Golden Gate Bridge at twilight, and we go on. So this is the Grand Canyon at sunset. And I should say what this is all about, and that is that those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies that can significantly increase one's chances of making such a discovery? Now, I guess, I discovered superfluidity in helium-3, and that was clearly a discovery. It wasn't something that I had set out to do, but in fact I looked with rather keen eyes at what nature was telling me. So let me illustrate this with a linked chain of discoveries and inventions, starting with this person here. This is kind of a fascinating tale. This is James Dewar. And of course, we all know that Dewar invented the Dewar flask, amongst other things. Dewar was actually in what I would say not a terribly friendly competition with this gentleman here, Heikki Camerlionis, to see who could first liquefy the lightest and most inert of the atmospheric gases. And it looked like we're going in the wrong direction. It looked like Dewar had won when he succeeded in liquefying helium, what he was really trying to do was basically find the temperature where all of the atmospheric gases became liquids and the temperature at which those liquids solidified. And it turns out, of course, that helium remains as a liquid all the way to absolute zero. So there was this problem associated with that. So Dewar managed to be the first person to liquefy and later solidify hydrogen, the lightest of the atmospheric gases. Helium is heavier than hydrogen, but also more inert. Camerlionis then set out to liquefy and solidify helium. However, no matter how low in temperature he cooled his liquid helium, he was never able to get it to solidify. Indeed, I have cooled liquid helium-3, and the only reason I'm saying helium-3 is because liquid helium-3 is a very good thermal conductor, whereas liquid helium-4 is not a very good thermal conductor at low temperatures. Anyway, so I have cooled liquid helium-3 down to 1/10,000th of a degree above absolute zero, and it stays very happily in a liquid state. The reasons for this were, of course, not well known to Dewar and Onus, but had something to do with the uncertainty principle. Eventually, Camerlionis gave up and looked around for an interesting question of the day that he could answer with his complex refrigeration device. People had argued what would happen to the electrical conductivity of a very pure metal if one could cool it down to nearly to absolute zero, and Onus decided to answer that question. Onus got a very pure sample of mercury and instructed his associate, I suppose this is his technician, to measure the electrical resistance of the mercury as a function of temperature. So this is temperature 4.5 degrees down to 4 degrees Kelvin, of course. And you can see that in fact, as he is cooling, the resistance is dropping, which is what you'd expect, of course. But then, at a temperature of about 4.2 degrees, the electrical resistance dropped precipitously to a value that was essentially within the limits of their measurement, to 10 to the minus 5 ohms. This, of course, I mean, we look at that right away and we all realize, this was the discovery of superconductivity, and that's exactly what it was all about. But you can't imagine, I mean, I suppose I can imagine better than you can, the excitement, suddenly knowing that something like that has happened and that you were the first person to see it. That's one of the reasons why being an experimental physicist is such an exciting thing, at least for me. So the relevant research strategies that allowed this discovery to be made, first of all, use the best instrumentation available. You're going to see that over and over again. It always pays to have the best equipment you can, but that don't reinvent borrowed technologies you can. In this particular case, Dewar had invented the Dewar flask, and Camerlionis was quite happy to use that technology in his own experiments, even though these two were bitter rivals. Look into an unexplored region of the physical landscape. That's really a good way of finding new behavior never anticipated. And failure might be an invitation to try something new. I mean, I think to say that one fails in science simply means that it's time to go on to do something else. And finally, be aware of subtle, unexplained behavior. Don't miss it. And there are so many cases where particularly young graduate students thought they knew what they were looking for, and when they saw something that they didn't think they were looking for, they passed it up, and that may have been a much more important discovery than anything else they could have made. So this is Peter Kapitsa, who first showed that at temperatures below 2 Kelvin, liquid helium exhibited zero viscosity. This is superfluid helium-4. This was the discovery of superfluid helium-4, and Kapitsa shared the Nobel Prize for Physics in 1978 for his work in discovering superfluidity in helium, with two people I know very well, Arnold Penzias and Robert Wilson. These were people I knew at AT&T Bell Laboratories when I was there. Now, these two gentlemen discovered the cosmic microwave background radiation, and for this, they shared the Nobel Prize for Physics in 1978 with Kapitsa. Now, this is kind of an unusual Nobel Prize because it's not uncommon for people to share a Nobel Prize, but in this case, the discoveries were completely different. And so it's sort of an unusual event. So this is Arnold Penzias. When I was at AT&T Bell Laboratories, Arnold Penzias was my boss's boss's boss. So that shows where I was on the pecking order. And this is Robert Wilson, and these two gentlemen shared the Nobel Prize. I think what happened is that each one, no, I suspect what happened is that these guys each got a quarter of the Nobel Prize, and Kapitsa got half of the Nobel Prize. It's very complicated as to how these things work out. Well, I'm shifting gears now a little bit. AT&T was a place that was very concerned about radio noise. In particular, this is a picture, a very old picture of Carl Jansky at Bell Laboratories. Jansky was an engineer. AT&T was interested in finding out where this radio noise was coming from that was interfering with their signals. And so they asked Carl Jansky to find out where it was coming from. And what he found was it was coming from up there. So that's really, I suppose, the start of radio astrophysics. Eventually, AT&T got to the point where they were interested in seeing if they could mediate telephone conversations using satellites. And I don't know how many people here have actually did that. It was not a very successful event. And I think the worst part of it is the satellites were in stationary orbits 22,000 miles high. And so there were long delays in the telephone conversations. So that didn't really work very well. But this is, in fact, a horn antenna. Horn antennas are quite nice because, in fact, they don't tend to couple to terrestrial sources of radio noise. But the thing that was really interesting about this was in this little shed, there was a spectacular preamplifier, thanks to this person here. This is Charles Townes. Charles Townes invented the maser. This is basically ammonia maser. It wasn't a technology which was terribly useful for telecommunications, but in fact, this pointed to where one could go rather. And so after Charles Townes, and this is Jim Gordon, created the ammonia maser, then Nicholas Bloomberg at Harvard realized that, well, gee, we can make a solid state version of this thing, which will work much better. And indeed, he did that. So this is now, we're really, this is Penzias and Wilson. Penzias and Wilson were very interested in looking for relic radiation left over from the Big Bang. And so they were looking, now back in those days, I should tell you that all the data came out on strip chart recorders. So if you're old enough to remember when data came out that way, well, it must have, it's a warm spot in your heart for sure. But basically what they're doing now is they were comparing the noise coming in from their antenna to the noise being radiated by a black body at some well-known temperature. That way they could make absolute measurements of this radio noise. So let's look at the relevant research strategies, and you're going to see they all end up being about the same. Use the best technology available. Don't reinvent the wheel. Borrow if possible. These are, you've already seen these before. Look into a region of parameter space that is unexplored. That is certainly a useful thing to do. And finally, understand what your instrumentation is measuring. Too often, people think they understand what their instrumentation is measuring. They get very excited, only to find that, in fact, it was actually doing something completely different from what they thought. So this is probably the most important bit of advice I can give you. So this is John Mather and George Smoot. Now, John Mather and George Smoot were basically got the Nobel Prize in 2006 for their discovery of black body form of an anisotropy of the cosmic microwave background radiation. And I think if you look at this, this is a spectrum that they got. It's the intensity now as a function of wavelength, and this red curve is a perfect black body curve with a temperature which is characteristic 2.725 Kelvin within 1,000th of a Kelvin. So this is looking at this relic radiation that was really left over from the Big Bang and characterizing it. And it has a characteristic temperature as I've shown up there. If you look at the anisotropy of this cosmic microwave background radiation, you can see that there's a dipolar effect. In one direction, it's hotter than the other direction. That's mainly because of the fact that the Earth is moving through this radiation. And you can get rid of that. And then once you've gotten rid of this dipolar effect, what you see is the plane of the Milky Way galaxy. And it's possible to get rid of that as well. And when you do, you're left with this wonderful, I would say, uniform fluctuations in this relic radiation that's left over from the Big Bang, essentially. This is actually, this was done, I can't remember what the time was, but this is the best that anyone's ever done. This is called WMAP. The W is for David Wilkinson, who sadly died before his experiment was complete. That's the problem in general, I would say, in science. You have to be healthy in order to live long enough to see the fruits of your labor. But this what we know now is, in fact, this is basically fossil radiation that's left over after the Big Bang. The universe started expanding, and the radiation that existed would Doppler shift back and forth from this expanding cloud of matter, and ultimately it started cooling, and so the characteristic temperature of this radiation as it cooled, and was very hot to begin with, is now roughly 2 Kelvin. So now I'm going to shift gears. This is another one of my pictures. This is the Iguazu Falls, which is just a spectacular waterfall. I agreed to give a talk at a liberal arts college in Paraguay, if in fact they would take me to Iguazu Falls. So there's two women that took me to Iguazu Falls, and one of them saw this black vulture and said, "Oh, get a picture of the bird." And so I waited until the bird flew in front, so that's why you have a black vulture in this picture. But anyway, so the process of it, getting back to the issue at hand, the process of advancing science often leads to inventions and technologies that directly benefit mankind. However, it is impossible to know from where the advance might come that might solve a particular problem facing mankind. Consider, for example, nuclear magnetic resonance. And now, I dare say I've used nuclear magnetic resonance throughout my research career, I would say. NMR was invented by these gentlemen here. Felix Bloch, some people would not call Felix Bloch a gentleman, but he was a very bright scientist for sure. Anyway, Felix Bloch was at Stanford University and Ed Purcell was at Harvard University. And these two, in 1946, invented nuclear magnetic resonance. And just 6 years later, they were awarded the Nobel Prize for Physics. And if you think that's the end of the story, it's just the beginning of the story. People began to use NMR. First of all, they were able to generate very homogeneous magnetic fields, and once they could do that, they could actually look at the interactions between nuclei, particularly protons, a lot of hydrogen in this thing. And those don't all resonate at the same frequency. And understanding why that's not the case, of course, was certainly a learning experience. Later, people were able to do much more sophisticated kinds of nuclear magnetic resonance, Fourier transform and two-dimensional NMR resonance. You learn you basically can go from this to something that looks like this, and this basically shows what the molecular bond lengths are. And for his work on specifically this problem here, the Fourier transform NMR, Richard Ernst was awarded a Nobel Prize in Chemistry in 1991. And I always like to say that he's smiling, but of course that's got to be the case. If you just learned that you won a Nobel Prize, you smile. So let's keep going. It turns out that Richard Ernst had a colleague. They were working together. They're both Swiss, but only Richard Ernst got the Nobel Prize. So I would meet these guys. Kurt Guthrie was the poor gentleman that didn't share the Nobel Prize. And I asked Kurt, I said, how did you feel when Richard Ernst got the Nobel Prize and you didn't share it? I said, you must have been disappointed. He said, no, I wasn't disappointed. I was mad. and so then Kurt Guthrie basically set out as a man possessed to show that he deserved to get the Nobel Prize too. And indeed he did. So this is Kurt Guthrie getting his Nobel Prize from the King of Sweden in 2002. And this is still, we're talking about NMR. This is, I don't know how many there have been a lot of people have gotten Nobel Prizes for advances in nuclear magnetic resonance. This is the last one. Now, I like to look at this, but then I don't like to look at it. This is a very healthy human knee. And one of my knees is titanium, and the other one is not healthy. But in fact, you can do spectacular job. You apply magnetic field gradients, and that gives you spatial information about where all the signals are coming from that are contributing to this. I don't know. I'm not patella. I think one of those is the patella. I have no idea where that is. But anyway, so you can get very detailed three-dimensional information using nuclear magnetic resonance. And for their contributions to NMR, Paul Lauterbur and Peter Mansfield shared the Nobel Prize in Physiology or Medicine in 2003 for their discoveries concerning magnetic resonance imaging. It's kind of interesting because I actually invented an early form of MRI, but it was only one-dimensional MRI, so I didn't learn very much. But I sent a preprint of that paper to Paul Lauterbur. And, there used to be a series of NMR meetings, and so I asked Paul Lauterbur if he'd actually gotten my preprint, and he said, yes, he did. I don't think it had anything to do with what he did later on. So this is the last contribution to NMR. This is, I think, really quite fascinating. There were two people, Seiji Ogawa and David Tang, who found that if you did MRI on active human brains, I'm not sure these are human brains, it's hard for me to tell, but those places that are processing information, the oxygenation state of the hemoglobin changes, and you can see that because in fact the spins then relax more rapidly in the deoxygenated state of the hemoglobin. So I was kind of hoping for a long time that this would be the, whatever it is, 5th Nobel Prize for NMR, but in fact it hasn't come. So I've gotten to the point where I've stopped hoping. But this had nothing to do with work that I did. I actually, as I said, I created an early one-dimensional and maybe a two-dimensional version of this, but it wasn't very exciting. So now I'm going to talk about my own discovery of superfluidity in helium-3, which occurred 1971 to 1972. I was a graduate student at Cornell University at that time. So let me go through a brief bit of history, not so brief. This is 1948. There was a guy named Ed Hamel who was at Los Alamos, who was responsible for keeping the nation's tritium supply clean. This was during the time when the U.S. and the Soviet Union were competing to see who could make the most lethal weapons and not use them, I suppose. That's an important thing. So Ed Hamel was responsible for keeping the U.S. tritium supply clean. And what that meant is that tritium decays with a half-life of 12.4 years. So periodically, Ed Hamel would purify the tritium. And what he's doing actually is removing the remnants of tritium decay, which ends up being helium-3, that substance that I love so dearly. And so Ed Hamel was, I think, well, he could have just thrown away the helium-3, but what he did was actually saved it. Then he liquefied the helium-3, and without getting any permission from the Atomic Energy Commission, he did that. And then he published his results. And not only did he publish the results, but he actually said how much helium-3 his sample was, which told the Russians something about how much tritium the United States had and how long they had it, because the tritium has to decay on half-life of 12.4 years. So that was quite an interesting story. 1950s, physicists studied the normal liquid behavior in helium-3. It is helium-3 atoms are Fermi particles. And so there's some kind of interesting behavior here. In 1957, of course, Bardeen, Cooper, and Schrieffer published their theory explaining the microscopic origins of superconductivity. And almost immediately, people predicted that superfluidity helium-3 would occur, and it basically would be a BCS superfluid, that is, superfluid having the kind of order that Bardeen, Cooper, and Schrieffer had proposed. 1965, John Wheatley, who was a very prominent low-temperature physicist, cooled helium-3 at saturated vapor pressure down to 2,000ths of a degree, but found no superfluidity. However, the availability of helium-3 led to new refrigeration technologies. In 1964, David Edwards discovered the finite solubility of helium-3 in helium-4. Helium-4 is a superfluid at these low temperatures. And in 1965, Henry Hall in England built the first helium-3, helium-4 dilution refrigerator. So these devices are, I think the commercial ones now cool regularly down to about 8 thousandths of a degree above absolute zero. So that's fairly low temperature, but in fact we can do better than that. This is a picture of showing how a dilution refrigerator works. You have a mixture of helium-3 and helium-4 in this. The helium-3 being lighter, if you pump on a mixture, most of what comes out, evaporates, is helium-3 rather than helium-4. And then you inject that helium-3 back and you have heat exchangers to cool it back down. It ends up here. This is called the mixing chamber. And as you are evaporating helium-3 atoms here, helium-3 atoms have to diffuse across this phase boundary between pure helium-3 and helium-4 rich phase that has a little bit of helium-3 in it. And that's basically how a helium-3, helium-4 dilution refrigerator works. This is a picture of my helium-3, helium-4 dilution refrigerator that I made as a first-year graduate student. So these are discrete heat exchangers which allowed us to cool the returning helium-3. This is the mixing chamber down here, and this thing would, I think, reach temperatures of about 15 thousandths of a degree above absolute zero. Below here is something which I'll talk to you about, another refrigeration technique which allowed one to get to temperatures which are much lower than you could get with a dilution refrigerator. So this shows there was, in fact, I call this Pomeranchuk's. Isaac Pomeranchuk was a member of the Landau School. He was a brilliant theorist. His main interests were actually in high temperature plasmas. But when he heard about helium-3, he started thinking about it. The liquid should have an entropy which decreases linearly with temperature, whereas the solid will have an entropy which is dominated by the nuclear spins of the solid. Each spin can point either up or down, and that gives you an entropy of R log 2 per mole. And eventually, at low temperatures, you start getting nuclear spin orbiting in the solid. But in fact, this was all conjecture by Pomeranchuk, but it ended up actually being the case. If you look at the latent heat of going from point A to point B here, it turns out that the latent heat is negative. It's a very strange system. And so you can actually use this process to get very cold, and that's basically how Pomeranchuk cooling works. And I don't know that Pomeranchuk's still alive. I suspect he wouldn't be. You can see this down here. This is the melting curve itself. There's a minimum in the melting curve where these two entropy curves cross. And so if you start pressurizing the liquid, you will go along this phase boundary to lower and lower temperatures, converting liquid helium-3 into solid helium-3, and thereby cooling. And you can get down to temperatures on order of 1,000th of a degree above absolute zero. This is a picture of my Pomeranchuk cell. And the helium, this looks, I put the helium-3 in sort of a golden color because it's rather expensive stuff. But in fact, and then we measured the pressure with a capacitive pressure transducer, remarkable precision. And this is actually a very highly reproducible process. This is superfluid helium-4, which is relatively cheap, but it has this wonderful feature that in fact it has zero viscosity. And so you pressurize this big bellows up here that forces the small bellows into this region down here. And then we measure the temperature by looking at the polarization of platinum-195 nuclei in a weak magnetic field. That's our real thermometer. And then you can calibrate the melting pressure versus the temperature. So this is actual data now, November 24th, 1971. And time, I think, is increasing, yes, to the right. Pressure is increasing upward. So I'm compressing the system, converting liquid to solid. Here, I rebalance the pressure transducer that measures the pressure, and I keep cooling. And everything is going well, and all of a sudden there's a sharp decrease in the rate of cooling. And I, of course, was very unhappy to see this. So this was I think the day before Thanksgiving in the United States. And so that basically gave me a 4-day holiday. And I said, okay, I will pre-cool the Helium-3 to as low a temperature as I can and try this experiment the next Monday. And so here I'm going a little bit faster, cool, 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 rebalance bridge, cool, cool, cool. And there is, again, this very sharp, well, it's not so sharp, decrease in the rate of cooling. So I allowed this thing to continue, and eventually I actually saw another tiny drop in pressure, and both of these features ended up being very reproducible. So here we have everything. This shows on cooling, we call this, we don't come up with fancy names. Physicists, I guess, maybe, I don't know. Someone has to be someone else. We call this the A transition, and this the B transition, and then this is the maximum pressure you could reach in the cell, and we just call that C, A, B, and C. And we could see these things both on cooling and on warming. The question is, what is this all about? So I invented an early form of MRI, which is to say that I applied a magnetic field that had a gradient to it. So the magnetic field was larger at the bottom of the cell than it was at the top. And then if I excite the NMR coil at a certain frequency, I will get a resonant layer where, in fact, the nuclear spins in the helium are in resonant. And if I sweep that frequency upward, this resonant layer will move downward, where the magnetic field is larger. And so I could basically plot out the distribution of solid and liquid helium-3 inside the cell. It's basically an early form of MRI. So this shows some early data. This is all liquid. Now, it turns out that the pressure transducer itself had created a magnetic field gradient. That's what this thing is about. But otherwise, this is all liquid. And then we start cooling, converting liquid to solid. The system cools. And so these are solid peaks growing up. So this is 20 milledegrees, 24 milledegrees, 20 milledegrees. Here we're down to 5 milledegrees. The solid peaks are very large right now. The liquid signal hasn't really changed very much. I've changed the gain of all the data back in these days was taken with a strip chart recorder. Nothing fancy. And so this is the liquid signal, and it all, the liquid was not changing in any way, just the solid peaks got bigger and bigger. This is real data now. And so time is, for some reason, increasing to the left and pressure is increasing downward. So these are these spikes of solid helium-3, as I said. This is the liquid signal, and I looked at this and I said, this should be flat across. Why is this distorted? And then when I saw this drop in pressure at what we call the B transition, what I found was, in fact, that the liquid NMR signal dropped by about a factor of 2. And this is August 17th, 1972. I tried this experiment a second time to make sure it was reproducible, and indeed it was. So this is April 20th now, 1972. At 2:40 in the morning, I wrote in my lab book, have discovered the BCS transition in liquid helium-3 tonight. Now, you cannot imagine how excited, in fact, even when I'm talking to you now, the hair on the back of my neck is standing up. It was such an exciting moment to realize, in fact, that this was something that people had predicted, but no one had ever found, and there it was sitting in my lap. It's really exciting. I think at 4 in the morning, I couldn't stand it anymore. I called up my thesis advisor. You better be sure you're correct if you call up your thesis advisor at 4 in the morning. Anyway, so it was, in fact, he agreed that this was correct. So let me just go through the strategies that allowed this discovery to be made. First of all, utilize new technologies. Pomeranchuk cooling was a relatively new technology. To view nature from a new perspective or in a different realm, and I'm talking about really very low temperatures. Don't give up when things are going badly. failure may be an invitation to try something new. And I think this is really good advice for almost anyone. And spend a little bit of your time doing something different that sounds about the same. Curiosity-driven research is fun, and it can be rewarding. And this is really an important one. I'm hesitating because I had a student, I won't say anything more, a graduate student that was quite interested in doing something that had absolutely nothing to do with the experiment. And so avoid too many commitments. The demands of good research do not adhere to a schedule. I mean, if you're in a laboratory environment and you're doing something, this is for a graduate student, this is a once in a lifetime perhaps opportunity to get your own Nobel Prize. No, to do something, to discover something new though. And then finally back off from what you're doing occasionally to gain a better perspective on the task at hand. We become myopic when we focus too tightly on our work. And I think that's true not just in low temperature physics, but everywhere. So now we're almost done. This is Osheroff's Pomerantsev cell, which I showed you before. But now I've put the names of people who have made contributions without any one of which probably I wouldn't be telling you the story today. Bardeen, Cooper, and Schrieffer, of course, they developed the theory that explained superconductivity, but Phil Anderson very quickly realized that same theory was applicable to understanding superfluidity in helium-3. Edwards and Hall, now David Edwards and Henry Hall very quickly realized that helium-3 could be used, in fact, as a refrigeration device. And so without that device, I probably couldn't have done the experiments I did, because you have to start at a very low temperature. This is Ed Hamel. Now, Ed Hamel was the person at Los Alamos who gave, I would say, the world helium-3 physics. It would have been very easy for him to take the helium-3 that he'd been separating out from his tritium and use it for something else. But in fact, he really did a lot for physics. I mean, helium-3 physics is helium-3, helium-4 dilution refrigerant is the primary way of studying things at temperatures typically down to about 10,000th of a degree above absolute zero. And here I put Bloch and Purcell because NMR is such an important probe for studying things at very low temperatures. So let me conclude by saying that advances in science are seldom made by individuals alone. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, we must support scientific research broadly. This was, I have to explain it at this point. I put this in when I was giving a talk for the National Science Foundation. I wanted them to support my research broadly, of course. And encourage scientists to interact with one another and spend a bit of their time satisfying their own curiosities. This is how advances in science are made. And so after all that, this is what happens, and it completely destroys your life. So don't let them give you a Nobel Prize. But here I am getting my Nobel Prize from the King of Sweden, and it is, I think, impossible not to smile at that moment. So there you have it. Thank you for your attention.
Quite a wonderful talk there. So I think Professor Osheroff, you must be very, very to take any question.
I would be happy. I will try to answer all of your questions.
Okay, so question
Does anyone have questions? Come on, you guys. This is a.
Come on.
Oh, here we go. You got someone in the front row.
How do you convince a granting agency to support your research? How to convince them?
Well, I must say that I think the National Science Foundation is the preeminent funding agency for this kind of work. So, I mean, if they weren't going to support it, the research would never have gotten done. But, you know, I dare say, I think now it's becoming harder and harder to support this kind of research, if that's what you're talking about. Thank you. Good question. Bad answer.
Just wondering, at what point did you know that you wanted to go into physics, and what really motivated you or inspired you?
Oh, wonderful question. Thank you for that. You know, I guess I was, I think I was 6 years old. I got an electric train for Christmas, and my father was a medical doctor, so he would come home and take a nap before going back to the office. And during that nap, I managed to tear the locomotive apart because I was fascinated with the electric motor. And so my father sees this thing, and I think he just looked at it and said, well, that's what I get. and so, you know, my father probably was the person that most stimulated me stimulated my interest in science. Now, I dare say that said, I think later on he probably recognized that he created a monster because, I mean, I am lucky to have survived my childhood. Quite absolutely, it's really true. I mean, there was one time I had gotten a whole bunch of paper capacitors from the telephone company. I wired these guys all up together. And then I charged them up to 600 volts. And the idea was then to discharge them across the primary of a transformer. I was going to get lots of volts out of that thing. But before I did that, I just ended up discharging the capacitors across my body. And the next thing I knew, I was on the other side of the room, and I really had no idea how long I'd been there. So I didn't tell my parents about that one. Yeah, that's a good question. Thank you. Oh, here we go. Okay.
So today, if you'd be back in your 20s and you'd have to choose a new research field, what would you do?
Oh,
Win another
the trouble is, of course, that hindsight is 20/20, and so I've had, I think, a spectacular career. I would certainly not change almost anything that I've done in my career. So it's sort of difficult for me to know, but if I were starting all over again, certainly I think low temperature physics has been very exciting. You know, and I would say that probably I would have ended up in condensed matter physics, but not necessarily low temperature physics. Yes, here's someone. Yes.
What do you think about the importance of blue sky research as opposed to research driven by commercial applications?
Yeah, well, virtually everything I do is blue sky research, I suppose. And so that is, I think, look, you have to have some unfettered research. I even call it blue sky research or whatever. But I think that first of all, I think the people that do that research frequently end up developing new technologies. Certainly, graduate students, it's very stimulating to be able to get in there and do something and see something that no one else has ever seen before. I guess, and I would say that certainly the National Science Foundation will always support some of that kind of research. The issue is, I'm afraid, how much of it will they support? And you know, I'm a little bit nervous about that. But certainly, I think that things were a lot easier. It was, you had a lot more freedom back when I was a graduate student than my graduate students have today. Sadly. Thank you. Someone way up in the top.
How would you actually go about, well, this might seem an odd question, but how would you actually go about finding one of these undiscovered parameters where you should start looking for some sort of discovery? I mean, there.
Yeah, well, it's not a bad question at all. I mean, I would say that you know, it's hard to plan to look for something that you don't know is there. On the other hand, I think there are things that you can do which will greatly increase the probability of if you're finding something. And that is, if you're doing an experiment, at the same time, do something else with that apparatus, because you really never know what you're going to see. If you see something, don't stop there. Say, well, okay, what is that telling me, and what should I do next? So, you know, I think it's a fascinating world. I will tell you, the person that probably most influenced the way I think about research was actually my high school chemistry teacher. His name was William Hawk. Sadly, he's dead now. But I think when I got the Nobel Prize, I called him up and I said, "Mr. Hawk, guess who?" And he said, "Well, that has to be Douglas Osheroff." But of course, he knew that I got the prize, and he realized how important he was to me, and so it was kind of wonderful. But he had came in class one day, and he had a milk carton. Something was inside the milk carton, and he said, "Research is like trying to find out what's inside the milk carton. You can do a series of experiments, and every time you do an experiment, you're asking a question of nature. Nature has to answer your questions, but nature's answers aren't what's inside the milk carton, but rather something about what's inside the milk carton. And then you have to do more experiments asking, in order to constrain your interpretation of nature's answers to your previous questions. And so it's kind of a game that you're playing with nature. And I, most of my career, I have thought about that what I was doing in my laboratory in that context. So it's a fun thing, tricking nature into giving up her secrets. I mean, we all know that nature is a woman, I suppose, but it could be a man too.
Thank you.
Here's one about middle row near the right aisle.
Mr. Osheroff, I would like to ask, have you ever encountered a situation that you doubt yourself, whether you would find anything significant in your experience, and how do you overcome this depressing moments?
Well, unfortunately, it happens quite frequently that you don't find what you were looking for, or the experiment doesn't work. But I think if you're an experimentalist, you have to be prepared for that sort of thing, and if it doesn't work, you have to ask yourself, what should I do different in order to make it work? It's this business, I suppose. You're trying to cheat nature out of one of her secrets. nature doesn't want to give up these secrets very easily. And so you have to come up with very clever ways of asking questions, that is, clever ways of doing experiments. And you know, that's, again, that's the way I've thought about my own research. You know, when I was active, sadly, I'm not active anymore, but it's absolutely fascinating to come up with some way of learning something new about nature, and that's really what research is all about. One right here.
When you get experimental data that doesn't fit your expectations, how do you actually distinguish that there is something interesting and new to pursue from a simple glitch or problem with your experimental or measurement setup?
Well, that's part of the challenge, of course. Yeah, I mean, you hit the nail right on the head, I think. You see a result, and then you have to ask, is this what I expected? Is this, well, first thing you need to do is find out if it's reproducible. And secondly, you need to find out, generally, I would say, okay, so if this is what I think it is, if I change the parameter space a little bit, do I see the changes in the behavior that I expect? So I think that it's a series of questions that you ask and you answer by doing experiments. But you know, I still like, I love this idea that I'm tricking nature into giving up her secrets. That's for me, I still like to think about it that way. Oh, way up there. Okay.
Yeah, again. At a certain point, I mean, there must always be some point where you recognize a dead end and realize you have to move on to something else. Did you ever encounter that, or how would you recognize something like that?
Well, I think we all, if you're an experimental scientist, you have to have run into that from time to time. And you know, I think, you know, it sort of depends, I guess, on what kind of equipment you have. I mean, if you poured, you know, $1 million in equipment and find that the experiment doesn't work, well, I would go home and probably have a stiff drink at that point. But you know, if it's simply a matter that well, okay, look, do I have control of all the parameters, and can I vary things in order to you know, get myself back in the parameter space where this experiment is likely to work. And you know, that it's again, I think, you know, if you're an experimentalist, have to, I think, be more resourceful than theorists. Theorists have to be smarter, but experimentalists have to be resourceful. And you know, it's not uncommon that experiments won't work. It's not the norm, hopefully, but in fact, I don't think that anyone that I know, certainly not my graduate students, have been crushed by failure, because it just doesn't work that way. You are in control. You have the opportunity to change the parameters until they do work.
Thank you.
Yes, front row.
I have a question.
Oh, wait a minute, we're going to use it soft spoken. You have to be harsh. Okay, go ahead.
In the beginning of your speech, you said you are passionate in taking photos, and can you tell all of us, maybe we want to know why you are passionate in taking photos?
Taking photos. Okay, yeah, I guess it's my father was, I think, a medical doctor, but in his spare time, he would do photography. And so I started working in the darkroom, I think when I was maybe 7 years old or something like that. And I just, you know, I love photography. it's a combination of the photographs that you get are very nice, particularly nowadays everything's in color. That wasn't the case when I was young. But you know, it's just a really fun thing to do. And you end up having all these wonderful images when you get done. So it's a win-win-win situation. It's something that I think there's nothing that, of course you spend time doing it, but you're going to spend time doing something anyway. So my wife and I, we travel the globe with fancy cameras, and we take spectacular pictures. I don't know if I can get this one out. Hold on. And show. That's not the right one. It's not giving. Oh, here. Well, this will be good enough. I think if it opens up. What is this? PowerPoint. Quit. Okay. Save. I never know whether save is a good thing or a bad thing. Cancel. Destroy. Don't save. Okay, so this is it. All right. This is what? This is, oh, I know it. It doesn't, if you don't have Photoshop open, it gets, this is something new. I don't understand it. It wasn't that way before. So hold it. As soon as photo, you notice I'm still using CS3, by the way. I happen to like CS3. Now, this covered everything. But, here we go. Wunderbar, I think. It's coming. Okay. So this is a place called Zhōzhaigo, and it's sort of southwest China. But it's really, unfortunately, the colors on my screen are much better than the colors there for some reason. But this is a really amazing place, and the bottom of this lake is covered with this beautiful, I don't know, turquoise and a kind of a blue-green color. Anyway, so we just love doing photography. I should tell you that I think it was not this trip, but there were two trips concatenated. My wife is very good at injuring herself. So I can't remember what she did on this particular trip, but in fact, what did you do, Phyllis? Oh, that's right. Yeah, this is and it was amazing. So we had what happened was the Chinese, I think, felt that they didn't want a Nobel laureate to dismember himself or something like that in their country. So anyway, we had a driver and a whole bunch of people to take care of us. And so when my wife's thumb was twisted the back way, I mean, I almost went into shock when I saw it. They found someone who would basically, first they took x-rays to make sure nothing was broken. And then this guy, I was watching, kind of pulled, rotated, and plugged her thumb back in. And anyway, it's a fascinating thing. I recommend strongly that you don't do that. Anyway, so this is Zhōzhaigo, and it's if you're ever in that part of China, I strongly recommend it. It's a beautiful place. But there are a lot of beautiful places around. Do I dare, should I tell them that we're going to Galapagos Islands? Okay, we're not. No, we are. We're going to the Galapagos Islands. That should be fast. Photograph the blue-footed boobies. Yeah. Okay. Any other questions before I get in trouble? Way back there.
Professor Osheroff, how did your life, your research, change after receiving the Nobel Prize?
Oh, I don't know that the Nobel Prize. It's funny, when I got the Nobel Prize, the NSF didn't increase my grant award by so much as a penny. So it didn't have any positive impact on my research in the sense that I had more money to do things. I could hire more people. It was in fact no change at all. On the other hand, I spent so much of my time traveling around the world giving talks, such as this, which I dare to say I enjoy doing this kind of thing. I think that it's at least I like to think that it's something that is useful for my audiences. I don't know if that's really the case though, but I would say that I get less science done for sure than I used to, but I have more fun.
Thank you. Any more questions?
You did mention about theorists and experimentalists. What is your opinion about doing the theory or the experiments?
Okay, well, I am definitely not a theorist, okay, but I have many friends who are spectacularly good theorists. And I find that working with theorists is an incredibly productive way of doing research. So people like Phil Anderson and Bill Brinkman and all sorts of very good theorists. We work together very well, and it's certainly more productive for me, and I think it's probably very useful for the theorists as well.
If the student would like to do something in the condensed matter physics, would you like to introduce some new and interesting research area for them?
Well, so of course I am in condensed matter physics. There are, I think a young graduate student today, the first thing they want to do is start looking over physical review letters, because that's generally where exciting new results are published, and you get some idea as to what maybe you would be interested in doing. I would say, in addition to that, of course, most graduate students do not work by themselves. There's a group, and you get ideas from other members of the group. There are lots of places, of course, reading articles, and you get ideas. So I think there is certainly lots and lots of places where young graduate students can get ideas for doing experiments. I dare say that you can go talk to your thesis advisor and say, what do you want me to do to get my PhD? That is probably the least productive thing that you can do, because this is someone that is later you're going to want him to give you a recommendation for a job, and if all of the ideas that you have done have come from your thesis advisor, well, there's not much he can say positively about how creative you are. So I think it helps to, if you are interested in having a conversation with your thesis advisor, go in with some interesting ideas, And don't go in there and say, what do you want me to do? Because that's not an interesting idea. Capisce? Capisce, what is it? That must be Italian, is that right? It isn't? It is? Anyway, do you understand, I think? Okay. Yes?
Mr. Osheroff, I hope that this question is not so impolite. I just wonder that if you can tell us the story that how you met your wife.
Okay, all right. Well, so we were both new fresh graduate students at Cornell University. And I'm going to get in trouble with my wife. So I went, I think the only place where you could get something to eat was the women's graduate dormitory cafe. She's already shaking her head. Anyway, I walked into this whatever place it was, and there was this really pretty young Chinese girl sitting all by herself. So I quickly got some food and sat down next to her. And so we started chatting. And I can't remember the whole story, but after a while, she would have absolutely nothing to do with me. And I can't remember really how we got, I mean, she definitely thought I was a shallow Caucasian. In fact, I think those were her exact words, is that right? Anyway, but I was persistent, and so I think if you're going for someone that you think is worth the humiliation, go for it. You know, I suppose that you might give Phyllis the opportunity of giving a rebuttal. I think I'm going to get in real deep doo-doo for doing that, but give her the microphone. Let's see what she has to say.
Well, all I can say is, because I was kind of very concentrated in my study because I thought that my parents, spent all that money to send me abroad so I can I study instead of dating. So, so eventually, after refusing to go on a date with Doug, and I saw him with some other girls. So I kind of was walking, we were walking opposite directions in the graduate center. It's co-ed, not female. Anyway, so I told my roommate, so this is the kind of, she's really a very shallow Caucasian, who's, doing dating instead of studying, things like that. But eventually, also, he had a card which has all kinds of stickers for universities, like from University of, University of Washington, Puget Sound, and everything, Caltech. So I said, oh, well, at least he finally, after going to all those universities, he finished at Caltech. But those university stickers were really from his siblings. So that's not really a rebuttal, but it's sort of a fun part.
Anyway, we've been married for God, how long? Just let me say that I think we've had a wonderful marriage, and I think it behooves all of you that are are interested in sharing your life with someone else, you know, it's obviously a two-way street, which is to say there's give and take. But I think having someone in your life that you know that you love and respect, there's nothing that makes life better than that. Thank you.
I think it's time to. Oh, there's one more question. Okay, I think final one.
What would you say to inspire us in doing physics?
Well, all I can say is I mean, I'm an experimentalist, okay, but for me, tricking nature into giving up her secrets, or in any event, discovering new physics, is the most exciting thing that can possibly happen to anyone. And it's certainly well worth the pursuit. So, you know, I don't regret having become an experimental physicist or anything that I've done in physics. It's all been exciting, fascinating, challenging, and sometimes, of course, things don't work, but that's life. Thank you.
So I think it's time to close this wonderful talk and question time. So I think let's thank Professor Osheroff again with a big applause.
And I will start by saying, 今天天气好极了。